All right, today we're going to tackle a puzzle that seems pretty simple on the surface, but it's hiding one of the most famously difficult problems in all of computer science. We're going on an impossible road trip.
So, picture this. You're planning this amazing bike tour of Ireland. You're going to start in Dublin, and you want to hit Belfast, Cork, Galway, and Limerick before you loop back to Dublin. And your goal? Super simple. Visit every single city just once, and do it in the shortest distance possible.
So how would you solve it? I mean, really think about it. For just 5 cities, you could probably eyeball it, right? You'd kind of sketch out a nice clean loop, try to avoid crisscrossing all over the place. Seems pretty straightforward. But what happens when we start adding more cities?
Well, this little puzzle, it actually has a name, and it's one of the most studied problems out there, precisely because it looks so easy at first glance.
Yep, this is the famous Traveling Salesman Problem, or TSP for short. It's a classic problem that has kept mathematicians and computer scientists up at night for decades. The idea is simple. Find the shortest possible loop that hits every stop. Sounds easy enough, but as you're about to see, the finding part, that's the real monster.
And look, this isn't just some brain teaser for fun. Solving the TSP is at the heart of so many things we totally rely on. It's how Amazon routes its delivery trucks, how school districts plan their bus routes. It's even how a robot in a factory knows the most efficient way to drill thousands of holes in a circuit board. Anytime you need to figure out the best sequence of stops, you're looking at some version of the traveling salesman problem.
So, what makes this so incredibly hard? The trouble really starts when we try to find the perfect answer by just checking every single option. With every city we add, the number of possible routes doesn't just grow, it multiplies. Exponentially. It's what's called a combinatorial explosion.
For our little 5-city bike tour in Ireland, there are only 12 unique routes to check. You could literally write them all down on a napkin and figure out the best one in a couple of minutes. No sweat.
But what if we bumped that up to just 25 cities? The number of possible routes explodes to, well, this. That's 310 sextillion. It's a number so mind-bogglingly huge it doesn't even feel real. Trying to check every single one of those is completely, utterly impossible.
Let's take a real-world example. For the 2018 Winter Olympics, the torch relay had to visit 80 different places all across South Korea. So how on earth do you plan the shortest path for that?
I mean, just try to wrap your head around that. If you tried to brute force the solution, just check every single option for those 80 cities, it wouldn't just be slow. It would take longer than the entire lifespan of the universe. This is what computer scientists call computationally intractable. The perfect answer is buried under an avalanche of possibilities we can never dig through.
So, if finding the perfect solution is off the table, what do? Well, this leads us to a really fundamental trade-off that you see everywhere in problem solving. It's about deciding what you actually need. Is it something good, something fast, or something absolutely perfect? You know, in a perfect world, our magical problem-solving algorithm would have 3 properties. It'd be fast, so we get an answer sometime this century. It'd be general, so it works whether you have 5 cities or 5,000. And it'd be optimal, meaning it is guaranteed to find the absolute shortest path, every single time. It's just like that classic sign, right? Good, fast, cheap. Pick any 2. Well, for these kinds of massive problems, it's the same deal. You just can't have all 3. To get a fast and general answer, you almost always have to give up on the idea of it being absolutely perfect. And this is where we meet the hero of our story, the heuristic. Now, heuristic is just a fancy word for a clever shortcut or a rule of thumb. It's a strategy that says, okay, I'm going to forget about finding the one perfect solution, and instead, I'm going to find a really, really good solution in a reasonable amount of time. It's all about being good enough.
So what does one of these shortcuts actually look like? Well, let's start with maybe the most intuitive one. It's often called the nearest neighbor or greedy approach.
The logic here is dead simple. It's all about making the best possible choice in the moment, without worrying about the future. You just start somewhere, find the closest city you haven't been to yet, and go there. Then you just do it again and again until you've hit all the cities. It's greedy because it always takes the best immediate reward. Okay, so let's try this on our island tour. Say we start in Belfast. The algorithm just looks at the distances and asks, what's the closest city I haven't visited? Well, that's Dublin, 167 kilometers away. Boom, that's our first leg of the trip. From Dublin, we just do the exact same thing again.
So if we follow this greedy logic all the way through, always just jumping to the nearest unvisited city, we get a final route that's 985 kilometers long. And that was super fast to figure out. But here's the catch. Is it the best route? Probably not. The problem with the greedy approach is that it can paint itself into a corner, forcing you to make a really long, inefficient trip at the very end. It's a good solution for sure, but it's almost certainly not the perfect one.
Okay, so if the step-by-step greedy approach has flaws, what's another way to do this? Well, what if instead of building a route from scratch, we started with a complete but probably terrible route and just tried to fix it?
Here's how you can think about the two different philosophies. The greedy algorithm on the left is kind of like building something with Legos, one piece at a time. Local search on the right is more like a mechanic. It starts with a fully assembled but messy engine, and then it just starts tuning and tweaking it, making small improvements over and over until it runs better. One of the most famous of these mechanic methods is called 2-oct, and the logic behind it is actually really elegant. You start with a totally random tour, which is probably going to look like a tangled mess with lines crossing everywhere. The algorithm just looks for two paths that cross. Then it checks what happens if it uncrosses them. If that little swap makes the whole trip shorter, it keeps the change, and it just does this over and over, untangling the knot until it can't find any more improvements.
You can see the idea right here. A path that crosses over itself, like the one on the right, is almost always a bad sign. It's inefficient. The 2-opt algorithm is smart enough to spot these crossings, and it just performs a simple swap. See how it reconnects the dots on the left? Just by uncrossing those lines, it creates a shorter, cleaner loop. Simple, but really powerful.
So just how powerful are these shortcuts in the real world? Well, take a look at this. This is a tour that connects 13,509 cities across the United States. Now, finding this route didn't involve checking every single possibility. That would be insane. It was found using advanced heuristics, a lot like 2-opt. It wasn't instant. It still took the equivalent of 5 years of a computer's processing time, but it turned a literally impossible problem into a solvable one.
And that really brings us back home, doesn't it? This whole idea of trading perfection for something that's good enough so we can actually make progress, that's not just for computers. Think about your own life. How you plan your week, how you organize a big project, even deciding what to make for dinner. How often do we use our own little heuristics, our own rules of thumb, to get things done instead of getting stuck trying to find the one single perfect way? It turns out the logic for solving the impossible road trip is something we use all the time.